Afternoon, everybody who's joined. I think we will get started. So today we're going to be having a talk that sort of touches on two areas that we've heard from in these talk series over the years: TCP and protocol performance, but also programmable data planes. And we've had Jorge and Jose and a bunch of others from the University of South Carolina present over the years. This is a paper that Jose worked on and is going to be talking about, and it's going to be talking a little bit about some work on trying to improve TCP fairness by reducing RTT and how that overlaps with the use of flow completion time and some P4 tricks. So I'm going to turn it over to Jose to walk through this talk. He's asked that we hold questions till the end, but if you do think of one, just put it in the chat and we'll make sure that we ask it at the end. So Jose, if you're ready to go.
Thank you very much, Jason. Good afternoon, everyone. My name is Jose Gomez. I am a PhD student from the University of South Carolina. And today I will be presenting and talk about my work on TCP and P4. So today I'm going to present a system that is aiming to improve TCP fairness in non-programmable networks using P4-programmable data planes. And the roadmap for these presentations is the following. First, we are going to have a little background on congestion control algorithms. Then we are going to talk about the RTT unfairness problem. We are going to talk about the proposed solution and a brief overview of the system. And then we are gonna talk a little bit about programmable data planes and how we can leverage P4-programmable data planes as a measurement instrument in order to take actions in non-programmable networks. Then the proposed system architectures, we are gonna talk about the details of the proposed solution. Well, we'll present the evaluation topology and 4 tests. The first test is a basic case where we separate the flow and relocate the bandwidth. Then we observe how we can scale these tests with more flows and see the improvement in the fairness. Then we can see also the RTT reduction in a per Q basis. And finally, we have a extension of the system that will also separate short flows from long flows, so they don't their dynamics are isolated, and that will serve to conclude this work and to talk about some future extensions that we can apply in this work. So we all know that TCP is the end-to-end communication protocol that enables reliable communication over the internet. We have the congestion control within TCP. This mechanism dictates the dynamic of the sending rate, basically. Traditionally, congestion control algorithm use the additive increase, multiplicative decrease approach, which basically linearly increase the sending rate until there is a congestion event where the sending rate is multiplicatively decreased. The key point here is that the sending rate increase as a function of the round trip time, meaning that you have a traditional congestion control algorithm. The longer the RTT, the longer it takes to increase the sending rate. That's on one side. On the other side, we have newer congestion control algorithms such as VBR. VBR follows another approach and does not consider packet losses in order to determine the sending rate. Well, the approach here in order to inject data inside the network is performed as a function of the RTT and the bottleneck bandwidth. Basically, VBR tries to estimate the bandwidth delay product in order to inject data. And here, the key point is that the descending rate is governed by the RTT. In this case, the higher the RTT, the higher the VDP, and more data will be injected inside the network. And that difference with the traditional congestion control algorithms approach takes us to the RTT unfairness problem. RTT unfairness problem occurs when two senders located at different distance or at different propagation delays from a common receiver share a bottleneck link. Here we have the case host H1 and host H2. Let's assume that they are in different locations. They are the senders. Host H1 experience a low RTT, whereas host H2 experience a high RTT. For example, if we are using cubic, the results will indicate that the performance favors flows with short RTTs. With VBR, it's the way around. The performance, the throughput, the flow that grabs more throughput from the available bandwidth is the one with longer RTTs, which is the case that we have in this figure. We have a short flow or a flow with a short RTT, 1 millisecond. It occupies practically the full available bandwidth here. After a flow with 80 millisecond RTT joins, and that will take dominance. So this is a problem, and this differs from the traditional congestion control algorithm dynamics. Particularly in BVR, this bias has significant implication for how internet protocols are designed, because there is a trade-off between low latency and high delivery rate, and this undermines the engineering efforts to reduce end-to-end latency. For instance, protocols like OSPF that prioritize routes with lower RTT will behave in all the opposite. So in that scenario, flows along routes are easily overwhelmed when competing with other taking suboptimal routes that have higher latency. In this case, VBR with higher latency, VBR flows with higher latencies will occupy more bandwidth. And another issue is that this creates a vulnerability, which is basically there could be malicious receiver that artificially inject the inbound RTT of their flow with higher latency in order to grab more bandwidth. Basically, a receiver can inject emulated delay using a temp if the transfer is performed over VBR, using VBR as the congestion control, and that will practically can overwhelm the bandwidth. Therefore, we propose a solution using P4-programmable data planes to address this RTT unfairness issue and enhance the performance of different TCP congestion control algorithms. In this case, we use P4-programmable data planes as a measurement instrument to capture passively the traffic. We are not interfering with the network here. We are just passively getting a copy of the traffic between legacy devices. And I just want to mention that this is like a use case of a bigger picture where we can, from the science CMC perspective, we can also consider other metrics by extending this system in order to calculate, for example, packet loss and the latency or the added latency due to queuing delay. We can also measure the throughput on a per flow basis in order to assign custom policies and perform flow separations, find the optimal buffer size, and also we can integrate this with Perf in order to have more granular measurements and perform actions in non-programmable networks like the traditional networks that are widely adopted and we usually operate. So this is the key point here is that we are not disrupting the current infrastructure. But in this case that I am presenting today, we are just computing the RTT of individual TCP flows, and we employ a classification algorithm to enforce flow separation. Basically, we measure the RTT, we perform the separation based on a certain criteria, and we allocate these flows in different queues so we can minimize the interaction that are result of the dynamics of these TCP flows. So that's basically the general overview of the system. And this is the proposed solution. We use passive taps, optical taps to collect the traffic and send a copy of the traffic to a legacy, from a legacy network to a P4 switch. Here we have a legacy router. We have the inbound traffic, and we collect the data here by adding a passive tap. We get the copy of the traffic, and we send that copy to the data plane of a P4 switch. In this specific system, we do the metrics computation, we calculate the RTT, and we identify the flow. That's performed in the data plane. Then the metrics are sent to the control plane that will execute a classification algorithm and do the queue assignment. The control plane will generate the rules that will be implemented in a legacy router. These rules are propagated or broadcasted to the legacy router through the management link. And that's the way that we enable programmability in legacy network or non-programmable networks. So this is the proposed system, the proposed approach. There are other issues that we can solve as well. We can measure the throughput and solve the queue imbalance problem that happens when, for example, TCP flows are underutilizing the allocated bandwidth. So we can extend the system to many other applications as well. A little background on non-programmable networks. We know that all the functions and APIs that we have in legacy networks or non-programmable networks are predefined and provided by the vendor. So the issue is that we lack from accurate visibility of network events, and this is a bit difficult for TCP to see what's precisely happening and have a timely feedback for governing the behavior of the network. Legacy networks, as I mentioned, provide an inaccurate, incomplete congestion feedback. Traditional congestion control algorithm, in that case, as they don't have a good visibility of the network events, they might result in unfair resource allocation. There are current solutions using active queue management algorithm, but the problem is that these require frequent reconfiguration and they usually tackle the problem in a general approach and does not allow modifying, and they don't have that much flexibility as the one that we have with P4-programmable switches, which those who are unfamiliar in P4-programmable switches, we can perform actions over network packets in a very granular ways in a per packet basis. We can change the way that we process packets in a data plane with a P4 program. We can create processing functions according to specific requirements, and have a very precise measurement of event in the data plane. And we are now using the P4-programmable data plane in order to measure the RTT, identify flows, and perform actions in non-programmable networks. How do we do that? This is the proposed system architecture. Here is where we zoom in into the system. Here we have the legacy router and the P4-programmable switch. Here we have the egress interface of the legacy router. We use optical taps in order to collect the data from the link between two non-programmable routers. We send these packets to the data plane of the programmable switch to perform flow identification, RTT calculation, and that's something that is performed at line rate. And after we have the RTT sample, we send that sample to the queue assignment or the classification algorithm that will perform the queue assignment. After that, the control plane will generate the rules that will be installed in a legacy network through the management port. In this case, we are using a Univ router MX204, and basically we create we use the APIs that Univ provides in order to tell, okay, I want to classify a flow with this IP into into a specific queue. In this case, we specify the limits, the lower and upper bounds for the queues for each queue. And also we have the default queue, which is for the short flows or the flows that are to be assigned to a specific queue. And that's how basically we assign the flows. And finally, the system also resizes the buffer size following the Stanford rule, which reduces or sets the buffer size as a function of the BDP and the number or the square root of the number of flows. So because we know the RTT, we took the RTT that is the average for each queue, and we use that metric in order to resize the buffer for each queue. And that way we minimize the extra latency that is caused by queuing delay. So this is how basically the system works. And let me explain a little bit how we perform the RTT calculation, which is, this is not our work, this is Shen's et al. Works that basically measures the RTT in the data plane. But we changed this program a little bit because this is using an inbound P4 switch. We are using here a P4 switch that is a measurement instrument. It's not receiving that, it's not performing any action from the traffic of the network. So what happens here is that for each outgoing packet, the system computes the flow identifier of the packet by applying the hash function that consists of the source destination IP, a hash function on the phi tuple that consists of the source and destination IP addresses, source and destination port numbers, and the communication protocol. In addition to that, we calculate the expected acknowledgement, which is basically adding the payload length to the sequence number. And these are the keys of the data structure that we are using for the timestamps of the outgoing packet. When we receive the incoming TCP packet, the system uses the flow ID and the acknowledgement number to search for that match, see the timestamp, and after there is a match, we can generate an RTT sample. And that RTT sample is the one that is sent to the control plane. In addition to that, we also implement a count mean sketch data structure to estimate the packet count for a specific flow. This is to differentiate long flows from short flows. This is how we can identify long flows from short flows as well. So once we have the RTT sample, now it's time for the control plane to operate. And here is where we implement a classification algorithm, which is the Jenks natural breaks algorithm, which basically groups the RTTs that are related to each other into a group, and that group will be assigned to a queue. For example, we have, let's say, some flows with low RTT, let's say 1, 2, and 5 milliseconds. And then we have another group of 20, 25, 30, 35 milliseconds. What the Jenks natural break algorithm will do is will separate uh, these two groups and provide us the boundaries for each group. And those boundaries are the ones that are used by the rule generator process in order to set the flows to a specific queue. So that's basically how we classify the flows. Finally, before jumping into the results, we have the evaluation topology, which is basically implemented with two legacy routers, a P4 programmable switch, which is the edge core Tofino switch from Intel. We have two servers with enough resources, so the CPU counts or memory are not the bottleneck. In these experiments, we try up to 100 flows. We use optical taps in both directions for the transmitted packet and the received packets for 2 ways over a 10 gigabit bottleneck link. And as I already mentioned, the control rules are propagated to the Juniper router, the non-programmable router, via the management link. And for reproducing multiple hosts, we basically use Mininet. We have several senders, an Open vSwitch, and that Open vSwitch is bridged to the NIC of the Lenovo server, which is basically a Connex X5, which is up to 100 gigabits per second. So that's basically the proposed evaluation topology. And now we can jump into the results. So this experiment corresponds to cubic flows, and we can see on the left-hand side on this figure, this is the natural behavior of cubic flows. We have one flow that starts, then the other flow joins, and as expected, it takes some time to convert to or try to convert to a fair share of the bandwidth, which is the case for the third and fourth flow joining here. We can see that these flows have different RTTs, and they cannot reach a fair share, or it will take a long time to reach that fair share. However, when we implement the flow separation, we can see that as soon as the flow joins, we can immediately allocate or relocate this flow to a different queue. In this case, let's say the increase in the sending rate is practically faster, and the bandwidth is divided evenly between the competing flows. And in this case, we see that the system can improve fairness. Let's see what happens with VBR. In VBR, the problem is that we have a flow with a low RTT. When a flow with higher RTT joins, that will take dominance. So that will basically grab uh, the major part of the bandwidth, and so on. So the flow with higher RTT will get the higher bandwidth in this case. With the flow separation, we can enforce a policy that will evenly distribute the allocated bandwidth according to the RTT and enforce fairness independently of the congestion control algorithm that the flow is using. So that's for test number 1. This is a basic case. We also tested with more flows, with 100 flows, to see how the fairness can be improved. In this case, we have 100 flows, and as described before, the P4 switch implements the Jenks optimization method to group the closely related RTTs in a specific queue. And we can see that for cubic, we have an improvement in the fairness with separation, which is not the case when we let them share the same queue. On the other hand, BBR has a similar result with separation, and without separation, we already know that the flow with higher RTT is dominant. We also measured the RTT in a per queue basis for the previous experiment. So in this case, we have 100 flows. They are assigned RTTs from 1 to 100 milliseconds. In a scenario without separation, where all these flows are sharing the same queue, we can see that the trend is to have an additional delay due to queuing delay. And this delay will settle around 100 milliseconds, which is uh, the buffer size of the queue that is configured in this experiment. So independently of the RTTs of the other flows that join and or share the bottleneck link, the r the r the round trip time, the final RTT will tend to be the highest. However, if we separate them in different queues, we can see here that the first group of flows that has initially 20 milliseconds, they are allocated into a specific queue and they experience around 35 milliseconds. When the other flow joins, the other group of flows with higher RTT, in this case, initially they have 50 milliseconds, they settle around 60 milliseconds. And subsequently, the other group of flows with 70 milliseconds will settle around 81 milliseconds. And finally, the one with higher RTTs, which is configured with around 100 milliseconds, will settle around 105 milliseconds. So that's basically the advantage of separating the competing flows into different queues. In addition to separating long flows from each other, we also separated short flows from long flows. So in this case, as I mentioned before, we use the count meet sketches in order to identify long flows and separate them from short flows. We can use the capability in the P4 switch in order to improve the flow completion time of short flows. And short flows in these experiments resemble web browsing competing against large data transfer. We can see here the flow completion time of short flows is reduced with separation. However, without separation, we can see that the transfer will take longer because of a buffer bloat. or the additional delay that is produced by the queuing delay. So without separation, basically, at least 60% of the short flows takes more than 0.49 seconds to complete, and the RTT settles around 130 milliseconds for this experiment. But with separation, this value is reduced to around 0.17 seconds, and the RTT to around 25 milliseconds. With this approach, we can improve the quality of service also of delay sensitive applications. And there you have it. I just want to finalize this presentation with the contributions and some future work. You observe the preliminary results of a system that segregates TCP flows based on their RTTs. Of course, this system could be extended to compute other metrics like the packet loss, the queuing delay, and the throughput of individual flows, and perform actions in non-programmable routers. We also observe that the impact of RTT unfairness was reduced. The system can perform these improvements independently of the congestion control algorithm. We observed some improvements in the flow completion time, in the RTT of the competing flows, and the system can enhance the quality of service and improve network efficiency. Finally, the system can be extended to measure the throughput and combine it with RTT measurements to create custom policies. This is like a future work that I am currently working on. And besides that, we can also evaluate the system performance using real world traces like the MAUI traces or the CAIDA traces. All right, I will stop right here. I don't know if you have any questions or comments here. I will be happy to answer them.
All right. Well, thank you for going through that talk. Really, really comprehensive, Jose.
Thank you.
So I've given everybody the ability to unmute yourselves if you do want to raise a hand or unmute and ask any questions, or you could, of course, type it into the chat room. I have a couple that I've just kind of jotted down here. So understanding that this is very preliminary work. So, you know, if you don't know the answer, certainly just say so. Where do you think this system would be best deployed? Have you given some thought if this is something that is going to work best in like a backbone network core or within a regional network, or is this better deployed and sort of categorized close to where the workflows are going to originate within a campus environment, or does it have to be all of them?
Well, I think this system could be deployed in any of those mentioned environment without causing too much disruption because basically we are passively tapping the traffic and performing actions over a non-programmable network. Realistically, and I think that's something that is included in the future works, this is very suitable to test them in the SIAM-CMC context where we have long flows, data transfers, and different RTTs. So I believe that a good starting point will be deploying this system in the SIAM-CMC and see how we can improve data transfers, large data transfers, so people stop shipping hard disks, as you mentioned, Jason.
Okay.
I will add something there. Jason, this is Jorge. This is Jose's work, but here at the USC group, we are in the very early phases of implementing in our science DMC, not necessarily with RTT unfairness yet, but there are other metrics that we can improve. For example, adjusting the buffer size according to the round trip time of the flows. As we know, the buffer size of a router depend, if we want optimality, depend on the round trip time and other parameters. So we are in the early stages. We receive an NSF CC Star grant, and we will be reporting, hopefully in 1 year from today, the first results of this being implemented in USC, University of South Carolina Science DMC. I can provide more details, by the way, if needed.
Okay. Well, thank you for that extra info, Jorge. I don't see any other questions yet, so if anybody does want to raise your hand or unmute or chat, certainly do so. So I had another one. So since you're still sort of in the period of testing this, how long until you have sort of enough data on a specific flow before you're able to sort of make a choice about its categorization? Are we talking sort of milliseconds to converge or longer than that?
This is, as I explained in the RTT calculation, this is basically performed at line rate. And actually, the bottleneck in setting or performing the actions in the non-programmable router, I didn't measure, but this instantly, I will say less than 1 second. In less than 1 second, we calculate the RTT, identify the flow, the classification algorithm, create the control rules for the non-programmable router, and these rules are implemented, and you can see the effects immediately. So it's not like it takes long. But I have to mention that this was tested up to 100 flows, meaning that the scalability of the system and what will happen if we have many more flows, this will impact in the decision to relocate flows.
Okay.
So I see a question here.
I'll read out Julio's question. To impose fairness, did you encounter any conflicts or overhead with the CCA algorithms?
Well, yes. In this case, you can see the VVR is very dominant. Although I haven't tested it yet, I think that we can also use this system to improve the coexistence between cubic and VVR, which are two congestion control algorithms that have different design principles. So there is definitely it's well known. It's well known that VVR and cubic they don't coexist very well, and isolating their performance could be a good approach in order to improve fairness. For that purpose, there are some works of Dr. Fure, who created a system using P4 in order to identify the congestion control. In this case, it's just the identification. We can complement that congestion control identification with flow separation in order to separate congestion control algorithms in different queues according to their design principles.
All right. Well, I'll ask one more time. If anybody does have any other questions, you can either raise your hand or unmute yourself or put it into the chat room. And so far, it seems like you know you've done this with the Juniper that you said. I'm assuming that future work you'll try this on other forms of non-programmable switch of different sizes to just ensure that everything holds true for those assumptions.
Yeah, I think the limitation to try this specific system in another legacy device is to see if they allow us to set ACLs in order to separate flows in a per queue basis. So we should be able to create multiple queues. And then we should be able to, the router should allow us to create the ACLs in order to relocate these flows in different queues. That's basically what is needed in order to perform these actions, because what is missing in the legacy router is the RTT measurement. So we cannot measure the RTT, but we can derive a copy of that traffic to the P4 switch in order to perform that action, and other metrics as well.
All right. Well, I think that that's it for questions. Oh, nope, we had one more come in. Can you please comment a bit more about the challenges on validating the proposed system on real-world scenarios? Is it because of the lack of traces or environments?
Basically, I am currently working on validating the system with real traces. In this case, I am using the MAUI traces that are posted almost in a daily basis, and basically it's just obtaining from the traces the RTT of individual flows and reproduce that with mininet. The problem is that you have to create many mininet instances. Also, you have to make sure that your server has enough CPU, so that's not the bottleneck. And yeah, it's just playing with TCP trace and extracting the RTTs for individual flows, having the starting point for each flow, the flow duration, and with that one we will be able to reproduce the real traces. So I am currently working on that.
I will add to that, Jose, and let me see if I can share the screen. Thank you, Italo, and thank you, Julio, for those questions. Let me see. It's hard, at least at the University of South Carolina, it's hard to try to test with the real environment because we don't want to disrupt the enterprise network, the network where all the students are. And it's this network that we're calling Campus Enterprise Network here. But we have the commitment of the IT to work with us and implement these ideas in the Science DMC. That doesn't mean that the Science DMC is not important. We don't want to create problems, but I believe that this approach is first implemented in the Science DMC and then slightly into the enterprise network is safer. So what we're planning to do is to replicate the system that Jose showed in his test, but this is a real Science DMC. And if you see here, the optical tabs feeding the P4 switch, and then this P4 switch will reconfigure the core switch in the Science DMC. So this will be the real environment. What are the challenges here? I think we have everything because the core switch is the Juniper, similar to what the router Jose was referring to. So we don't see any technical challenge. The most certainly is a lot of work, but hopefully we're going to be able to replicate in the real scenario. Most important is not to create problems for researchers, for students who are using the network. We have to be very careful in implementing these ideas in real world. And our plan is from now to next year, we will be deploying in the Science DMC and then hopefully in the campus enterprise network. One last thing, notice that these are passive devices. These are passive tabs. We are not putting inline, and that is on purpose. That is on purpose. So if there is anything that was not expected, it's just a matter to disconnect the tab or simply not configure dynamically. So just disconnect what we put is very easily. Italo, I hope that answered your question.
Yep. Okay. Well, thank you for that additional information there, Jorge, and sharing a little bit about what you're thinking about in terms of campus deployment. So I'll thank you both again. Jose, if you want to send me the slides, I'll make sure those get posted along with the recording. And then for everybody else who's still on, we're going to have 2 weeks of Perf Sonar talks. We're going to have a talk about the 5.1 release next week, and then following week, we're just going to have another one of the Perf Sonar office hours where people can bring in their questions or have the Perf Sonar team help them with configuration questions or software questions. So hope everybody has a good weekend, and we will talk to everybody next week.
Thank you.